We'd like to welcome all of you to this month's TCIPG seminar series on resilient power grids. As you know, we get together on the first Friday of every month in order to bring in a speaker of national renown to talk on this topic, which we think is a really important topic and continues to grow in importance. We have had up to now in our series external speakers, external from the TCIPG Center. But today I'm really pleased to be able to introduce Tom Overbye as our speaker. Tom Overbye is one of the principal faculty members in our TCIPG Center. He's the Fox Family Professor of Electrical and Computer Engineering at the University of Illinois. And Tom was one of the people that was on the ground in the commission that was investigating the August 2003 blackout. So he has firsthand knowledge of what happened there. He was a key person in writing up the report, the very long report that ensued from that event. And we've asked Tom to come back and tell us, looking back based on what we know now, looking back on how the grid has changed and how cybersecurity has become much more of an issue even than it was then, what the knowledge about this blackout means for us. So without any further ado, I'll introduce Tom. And for those of you, there are two links for those of you who are the remote. If you logged in on the second link, which is the WebEx connection, you can ask questions, and we welcome questions. I think you've got a message that tells you how to ask questions, but if you raise your hand electronically as it is in the WebEx, then you can ask a question and we'll be able to page you through, we'll be able to hear your question and Tom can answer it. So I'd like to welcome you, Tom. Thanks very much for agreeing to do this.
Okay, thanks, Bill. As Bill mentioned, I was involved in the blackout investigation. I'll talk about that a little bit more as we get into this. I do want to say at the onset, I know there's a broad audience here. Some people out in the audience probably were involved in the blackout investigation and know quite a bit about it. Others might not even know that there was a blackout. Some are very knowledgeable of cyber systems, some are very knowledgeable of power systems, and a select few are knowledgeable of both. In giving this talk, the background is Bill asked me to give it because there had been some requests from various folks about talking about the August 14th, 2003 blackout, but I do recognize that it's rapidly transitioning from being a recent event to being more into history, but I think it still has a lot of things to teach us, so that's why I'm giving the talk. The talk's going to be about what happened then and leading up to it, but with the eye of how can we use this knowledge to help make for a better power grid. Not so much what are the immediate lessons from the blackout, because being almost 7.5 years ago, a lot of those lessons have been learned and put into practice, but look at how can it help us in 2011 going forward. For those of you who weren't here, it was a big deal, particularly for the folks in the Northeast and into Ohio, Canada. It did not affect us here in Illinois, but it certainly affected New York City and a lot of places. 50 million people overall were affected by it. This is a satellite picture. Initially, there was a really cool satellite picture that was much more dramatic, but that was showed to be a hoax. This one has proven the test of time that it's a legitimate picture of the Northeast before the blackout and after the blackout. I think that's from the night of August 14th. And you can see places like New York are greatly diminished, almost eliminated. A lot of the rest of New York is gone. It affected our friends in Canada as well. So there are a lot of people affected by this event. Just for those of you who don't know much about the blackout event, there's a wonderful report that was produced. Bill said I was involved in writing the report. I actually did not write any of the report. I wrote kind of event summaries and interview summaries from the on-site investigation, and then those got compiled into the report. So there are phrases occasionally that I can see in there where they say interview said, and I can see that was something that Doug Wiegman and I wrote down. But the report's wonderful, it's very accessible, and I would ask all of you to read it if you haven't already. It's written for a knowledgeable layperson. It listed 4 causes of the blackout. First Energy did not understand inadequacies with respect to their system, particularly with respect to voltage instability. That's the first one, and it's the most power system technical one. There was an interim report that came out that did not have this as a cause, but the final analysis, and it took quite a bit of analysis, said there were some voltage instability issues. The second one was First Energy had inadequate situational awareness. The third was their trees weren't managed properly. So that's why in the title for this talk I mentioned trees, because trees were very much a cause of this. They were ultimately the ones that hit the wire or got close enough to the wire to arc. So tree growth was a big one. And then the last was failure of the grid reliability organizations, primarily MISO, which is Midwest Independent System Operator, to effectively diagnose their system condition and provide the support to First Energy. A key takeaway from this is 2 of them, for sure, have a strong human-cyber interaction component, and we'll see that going forward. I do want to emphasize that in giving this report, or this talk, this isn't 2003, it's not 2004, it's 2011. We've come a long ways since 2003. The blackout report had 46 recommendations, many of which have dramatically changed the operation of the interconnected grid. Since this is a TCIPG seminar, I'll note that 13 of these were focused on physical and cyber security, and a lot of the NERC movement in this area was motivated by the blackout. So the focus on the talk is to look and say, what can this event teach us now as we go forward? I also want to keep in mind that this had a big economic impact. I've seen estimates of $5 to $8 to $10 million or $10 billion. So it was a pretty costly failure. Some say, though, that the yearly impact of blackouts just in this country is above $100 billion. So that's every year, just from the myriad of different blackouts that we see, many, most small. This is the First Energy Control Center today, or at least as of late 2000s. If you look at the bottom there, this is an image that I just tracked down online. They were in the process of changing their control center in 2003. I've visited since, and it's a really cool place. They very much have a big map board now, something they didn't have. And I should note that since 2003, there haven't been any big blackouts in their footprint or anywhere else in the MISO or PGM footprints. My involvement in the blackout, as Bill mentioned, was early on. The blackout occurred on August 14th. Like a lot of people in the power area, we spent a lot of time talking to reporters that first weekend after the blackout. Blackout occurred on a Thursday. I saw it on CNN, and I wondered, is this going to involve me? I was working at home that day. It was summer. The life was fun. And then by an hour later, the phone rang, and it was someone from NPR wanting to interview me, and then the phone just kept ringing. The next day, I went to the state fair because I had promised my wife and small children we would do that, and I spent most of the day at the fair on the phone talking to all different sorts of people. One that sticks in my mind is talking to a Chicago Tribune reporter, and she was trying to imply that the US grid was in bad shape, but Europe was in good shape. And I was saying, I don't think that's the case. But Italy had a blackout. They blacked out just about the whole country a month later, so it wasn't just us. But then I got tasked by DOE to do an on-site visit to First Energy on the Sunday after that. The people that went on that visit were myself and Doug Wiegman. Doug was a fellow UIUC professor. He was working in human factors. I wanted Doug on the team because we had to go interview everyone involved in it. And Doug actually had experience doing interviews. He was a human factors expert who used to work for the National Transportation Safety Board, and he'd be the guy who would talk to airline pilots who had survived failed crashes and the survivors and others who hadn't. So he had a lot of experience interviewing people. Doug said you got to get these people alone in a room to find out what happened. So what Doug and I did from August 19th to August 21st, well, actually we spent two days in that conference room pictured right there, talking to everyone that was in the control room at First Energy on the day of the blackout. And it was Doug, myself, the person, and their company lawyer. And I will say that First Energy was very cooperative during this investigation. We got the feeling throughout good hospitality and that they really wanted to help us understand what had happened. Did the same thing later on in MISO the next week, and then I was involved in a visit in October. By that time, the investigation had certainly changed. Maybe the tenor of the investigation had changed by October. There was a much larger cast of characters involved. When I was there in August, there were just a couple of us out in the field. By October, it was a major effort. I don't want to imply I played a big role in the blackout investigation, because I didn't. A lot of people did a lot more work over a much longer time period. I was only involved extensively early on, but I will say it was a very interesting early on time period. By the time Doug and I left First Energy on August 21st, we had a good feeling for what had occurred. That's the footprint from that day. The footprint just shows where First Energy is. They're in primarily Northeast Ohio, but with some of their service territories scattered throughout the rest of Ohio. Their neighbor is American Electric Power. First Energy was under the oversight of MISO. AEP, American Electric Power, was under the oversight of PJM. MISO primarily went to the west, so First Energy was their easternmost outpost, and at that time, I believe AEP was the westernmost outpost of PJM. Now ComEd is also in PJM. What I want to emphasize on this talk is on August 13th, people did not think we were headed for a catastrophe. If you were working in the power industry then, you did not wake up saying, I bet we're going to have a blackout this summer. I bet we're going to have a blackout today. I bet we're going to knock out the eastern part of North America. That was not the case. Certainly a lot of people after the blackout occurred would say how weak our grid was, but if you took a pulse of the industry at that time, we were feeling pretty good. Certainly as researchers, we knew there was more research to do, but it wasn't a feeling like we were on the verge of a catastrophe. I looked up the NERC 2003 summer assessment, which is available online. It listed some areas of the country as particular areas of concern. Ohio was not listed as an area of concern. The Michigan-Ontario interface, which did play a role in this, was listed in that document, but Northeast Ohio was viewed as pretty strong. I will say that one thing we found is if you look at that figure on the right, this is a voltage contour of what people expected the voltage to be across the Northeast. It's what they called the day-ahead model. And it actually, for the power system folks in here, it actually had what we'd call low voltage solution in the far eastern part of the model in the New Jersey area. It was just an artifact of the power flow solution. It was in what we'd call a voltage collapse situation. They had used that model all summer and didn't know it. Once we loaded it up and visualized the results, then it became apparent. That had nothing to do with the blackout. But it was just kind of funny when I looked at the model from the day-ahead case and I noticed that the voltages in New Jersey were down in the 0.7. Some of them were in the 0.6 range per unit. We had to investigate that. This is the First Energy control room. When I was there, I took a picture on my camera. I kind of blurred it a little to make sure I didn't disclose any confidential information. You've seen that their control center and newer pictures are available online. It was a normal day. August 14th, 2003, at 3 o'clock in the afternoon, I talked to the shift supervisor who left right before 3 o'clock. He said it was a good day. They had an outage of one of their generating units, but that was not particularly unusual. People were feeling good. And that was what people told us in the interviews. One thing from this diagram, which is noted in the blackout report, they did not have a big map board at that time. There's no map board shown on the wall there. And actually, if you look to the far left of the blur, way on the far corner, they had some strip chart recorders that stopped recording. And one of the issues in the blackout investigation is, well, why did nobody notice it? The reason nobody noticed is because the action was over here and the strip charts were on the part of the room that was not currently occupied. It had been a busy day at MISO, though. This is what it would have looked like if I had taken my glasses off. Again, I blurred it deliberately to make sure no confidential information is disclosed. They'd been very, very busy that day at MISO. The reliability coordinators, RCs, had started at 6 a.m. in the morning. They said they had problems in Wisconsin in the morning. And then at about noon, on this span here, this is a 345 kV, 230 kV transmission line. You can kind of see the wires there going over some nice trees. At 12:08 Eastern Daylight Time, there was a fault on one of these lines, and it actually tripped the 345 kV line and the 230 kV line. The tree was to blame, and they were busy dealing with that. I think they ended up blacking out, this is in Indiana, about 5,000 customers. But MISO was focused on this event that afternoon. We went to visit Synergy in October as part of the investigation, and Synergy, it was their line. They were trying to trim those trees that day. Back on August 14th, they said the property owner, who happened to be an attorney, was not interested in having them trim them. So it took them 2 months to get the trees trimmed. And this is the trees when they were trimmed. They trimmed them down to 6 inches. And I asked, can I show this picture? And they said, oh, yeah, sure. So that's a picture of the tree trimming. Hopefully those trees won't be causing trouble in the near future. So MISO was working the problem in Indiana. For those of you who work in the IT area and know about state estimators, at 12:15 they started having state estimator problems. What the report says was due to a combination of human error, and then a little bit later on there was a loss of another transmission line in Ohio that was a 345 kV line that also tripped because of tree contact. The human error, I don't know if it says this in the report or not, but one of the guys that was supposed to monitor the state estimator had, I believe, on his desk something that was supposed to notify him. It was an application running on his computer when the state estimator tripped, and he had turned off that application because it was sucking too many computer resources. Okay, so he just turned it off. But tripping a state estimator failing was not a major event at that time, but it did contribute according to the report. Also, something that I know is near and dear to Pete Sauer's heart, in Northeast Ohio at 1:30 in the afternoon, East Lake 5 tripped because of some reactive power issues associated with their exciter. That reduced the supply of the power into the Cleveland-Akron area. Well, that was not unusual. First Energy picked it up right away, and they responded appropriately to it. What started to get unusual is an hour later, the tie line between First Energy and AEP, it's a 345 kV Star South Canton line, it tripped at 1427. Okay, it tripped and it reclosed, which means that it had a fault on a tree, was later determined, and evidently the tree got out of the way enough, trees can get out of ways, and it reclosed and it was fine. So the line went back in service, and they did not see that on their SCADA. The reason why they did not see it on their SCADA is it was back in service. Normally a trip and reclose would generate an alarm, but unbeknownst to them, about 13 minutes prior, their alarms had hung. Okay, so in the control room, their alarms had hung. The First Energy IT folks knew they were having computer problems. Part of the investigations, we were trying to track down who was where when. So if you think about it, we were there like 6-7 days after the event. How many of you remember exactly where you were 6 or 7 days ago? That's what we had to ask these guys. Okay, what time were you in the room at? What were you doing? and it got a little foggy for some people just because of limits on memory. I used to be an EMS engineer supporting a energy management system for a utility, so I could relate to these computer guys. Usually when our computer is screwed up and I was working on fixing it, I didn't want to tell the operators until after I'd solved the problem. So these guys were working on it, but they didn't tell the operators. At the same time, the operators were getting calls from their neighbor AEP, which owned the far end of the line, saying, hey, we had a trip and reclose on this. And First Energy said they didn't see anything. And the reason they didn't see anything is their alarms hung. There's actually recordings of these phone calls, although I guess they've never been made public, that came out of American Electric Power. But there was a discussion that this was a very unusual event, that First Energy didn't see that. Okay, so they sort of knew something was going on, but it didn't affect them. At least they were still thinking it was a good day. This is a high-level voltage profile of best recollection or best reconstruction of what the system looked like on August 14th at 3 o'clock in the afternoon. The red there indicates low voltage areas. You can see the red dot in southern Indiana. That was because of the problem that MISO was working on because of that tree contact. And then there was some lower voltage across Ohio, but it was not abnormally low. So a lot of discussion and investigation is whether that red in Ohio, which you can see in northeast Ohio, was permittable or not. And ultimately, the report concluded no, they were operating in a voltage insecure way. This is a map. If you had a bird's eye view of the flow of the power grid at 3 o'clock that afternoon, this is what you would have seen. You can see the green arrows there show the direction of power flow, and the size of the arrow is proportional to the amount of power flowing on the line. If I were doing this just to a local audience, I could show a computer simulation of this, and you'd see the flow of power coming up into the Cleveland-Akron area from what First Energy calls their river units down on the Ohio River. There was a lot of power coming in from the south. Part of the reason why is because the Davis-Besse nuclear plant, which is a nuclear plant on the western side of Lake Erie, was offline on a long-term outage. They had also lost East Lake. East Lake is visible up on Lake Erie, kind of towards the more eastern part of Lake Erie. So there's more power coming into the region, but it wasn't viewed in the control room as being particularly unusual. It was a good day. Well, then the Chamberlain-Harding line tripped. There were 4 main 345s coming into First Energy from the south. Chamberlain-Harding was one of those. That line tripped. That would be a significant event. The difference on August 14th is First Energy did not see it and MISO did not see it. And that's extremely unusual. Utilities don't miss 345 kV lines tripping, but they did. What's funny is it's not on the map, and the map's not there because I didn't want to disclose the ECAR map, but we looked at the...
Tom, why did they miss that?
Well, First Energy missed it because their alarms had hung, and the way they would be notified of an event like that is they'd get an alarm. And they were watching, they were paying attention, they were looking for alarms. And the alarms, they hadn't had any for an hour, or about 50 minutes at this time. MISO got it, and we got their alarm logs, and it came up on the MISO alarm log, but the alarm logs at that time were not prioritized, and there were many hundreds of alarms in that alarm log. I think the number was about 1,400 that day. So the guy missed it. I asked him, why did you miss it? He said, I just missed it. And I was like, yeah, of course you're going to. It's like there were 1,400 of them. You can't pay attention to everyone. And it did not come in saying that this line tripped. What it came in as 4 alarms that talked about 4 breakers opening. And that's just how alarms come in. So a lot of work has been done since then in alarm log prioritization so that people don't miss this anymore. But they missed it. What's funny is this line is not on the ECAR map, which is what MISO was using. It was certainly on First Energy's maps. It wasn't a new line. It was like, truth is stranger than fiction, because when I looked at this, it's like it's not on the ECAR map. And I've got the map to show it, but I just took it out because of confidentiality concerns. But it's not there. I'm sure it's on the current maps. So that line there, which is shown by the black circle as being tripped, that's the Chamberlain-Harding line. What that did is it caused a contingent overload. That red circle there, I don't know if you can make it out, it's at 106%. That line, it's the star juniper line, it wasn't overloaded, but it was contingent overloaded. That means that if this is a contingency overload, what it says is if the Hannah juniper line trips, that line will be overloaded. This is monitored, and it was being monitored via MISO that day with flow gate 2265. 2265 was monitoring the flow on FE's star juniper line for contingent loss of the Hannah juniper line. This is where we need power engineers and we need cyber guys that understand power, because to understand how this flow gate works, you need to understand the power grid. And normally you have something called a LODF, which is a line outage distribution factor. The line outage distribution factor says if the Hannah juniper line were to trip, how much of that flow would go onto the star juniper line. And normally the value is 0.361. 36% of the flow would go onto that line. If you work through the math here, when the Chamberlain-Harding line tripped, what should have occurred is that this flow gate should have had a value of 109%. And what MISO was doing very good that day was when a flow gate came up over 100%, they were on the phone like that. And this would occur a half an hour later, and they talked to First Energy lickety-split. They weren't on the phone because when that Chamberlain-Harding line opened up, that changes the LODF. And that required a manual entry. Somebody had to go tell the LODF calculator that the Chamberlain-Harding line is open, then it updates all the LODFs, and it would have updated the values, you can see in the first equation there, to 0.463. Nobody did that. So it didn't get updated, so the flow gate was showing at 98%. And you can look in the log, and there it is at 98%. It's right at the top, but they alarmed at 100%. So I titled this the bad LODF that may have blacked out the Northeast. If that value had been 109%, I have no doubt MISO would have called up First Energy and tipped them off at 306 or 307 or 308 that something was going on. Okay, this is where truth is stranger than fiction. 98% alarming at 100, and it was really 109%. Well, actually that line opens up at 1532, and now the flow gate says the correct value because you don't need an LODF. The line's open, and it goes to 107%, and right like that, MISO calls up First Energy. So this was the situation at about 1533 where MISO starts to call up First Energy and say, hey, you got problems. But First Energy does not know they've got problems yet. So they're getting some data from MISO, but they look at their alarm logs and it's like, we're not seeing anything, so they have to get back to MISO. The voltage starts getting pretty low at this time. So as you start losing lines coming in from the south, and this was the second line to the south being lost, the voltage went down. First Energy's customers and generating plants start noticing something is amiss, so they call into the control center. And they start calling in to the control center. What happens is First Energy's control center, over the next couple minutes, and actually into the blackout event, would get what the report calls mini phone calls. For those of you who are computer science people, maybe an analogy is a denial of service attack, although certainly there was nothing malicious in this. People were calling in saying what's going on. If you look at the transcripts, a local utility or a local business calls up and says, why is their voltage too low? And First Energy doesn't know. When I talked to the control center personnel who were there, and I said, well, what were you doing during this time? They said, we spent a lot of time on the phone. Why were you doing that? Because the guy on the phone might have the answer. Okay? They were answering the phone because it could be someone telling them what was going on. Even when we got there 5 days later, First Energy, at least what they were telling us, is they didn't think they were the reason for this blackout. It was not clear that they were the reason, at least at this point, and certainly not at this point, and even a couple days later it wasn't clear. Some other IT issues that had gone on, I mentioned MISO RCs, the reliability coordinators had gotten many hundreds of alarms. That's why they missed those 4 circuit breakers opening. Contingency analysis results were starting to overwhelm. Contingency analysis runs off a state estimator, and state estimator, it gives a solution to contingency analysis. Contingency analysis does a lot of what ifs. What if this line went out? What if that line went out? And it reports violations on all those. Normally there's not that many problems, so you can look at a page and get a summary. Now they got pages and pages of violations. They got a data overwhelmed situation. The state estimator had failed earlier that day. It would fail at other times because of the severe system stress. There were inadequate procedures for dealing with the state estimator failure. Actually, when the system actually separated at about 4:10 that afternoon, the guy that was sitting right in the front, the operating engineer, we asked him what he was doing. He was trying to set up a power flow program to mimic the system conditions. I have done that many times, and it can take a lot of effort to do. He was busy doing that. So by 1546, we had a situation where a number of lines had tripped. Actually, they had blacked out part of the Akron area at that time. There were low voltages across the system, but the bulk electric grid was actually hanging on pretty well. After the event, people were saying, the grid's rickety, it's not that strong. My feeling was, hey, you gave it 3 contingencies and it keeps on ticking. I thought this grid was pretty strong, personally. But that line down there, that one that's overloaded at about 106%, that was the Samus Star line. That line was cooking. We've actually done some post-analysis on that line, and we looked at the temperature on that conductor, and it was quite hot. Low voltages abound. Here's the Cleveland area is kind of up towards the lake, and they had pretty good voltages at this point. The Akron area had a lot of outages already. Stuff was starting to trip, but the grid was holding on. Part of the investigation was to look and say, well, what could have been done? Okay, the grid hung on for 25 minutes. What could have been done? The DOE NERC report said about 1,500 megawatts of load shed were needed. If you do the analysis as to where that load shed should be done, I've kind of done a contour there. Anything shaded in purple would be good places to shed load. So in essence, to save the grid, what DOE NERC said is you had to shed a lot of the Cleveland load. Okay, so you had to get rid of Cleveland, but they didn't know this in the control center at the time. And I said, well, why didn't you guys shed load? And the guy said, we wouldn't shed load if we didn't think it would help, which is certainly a reasonable answer. You're not going to willy-nilly shed Cleveland. So they didn't know what was going on. When we started the investigation, when we got to the First Energy Control Center and started interviewing people, we did not know the extent that their computer had hung up. And First Energy at that point, I don't think knew, this was like a couple days afterwards, I don't think they knew the extent to which their computer had hung up. We thought everything was working fine, except alarms weren't working. Turns out that their displays weren't refreshing very fast either. And if you're in a control center in a stressful situation and you try to load a display and it takes like 10, 15, 20 seconds, it doesn't sound like a lot, but if you start 1, 2, 3, waiting for that display to come up while the phones are ringing, people are saying, what's going on? That's a significant issue. And we didn't know this in the interviews, and nobody actually shared it with us in the interviews, but we didn't know to ask. We just thought the alarms had hung up. So the system hung in that situation for about 20 minutes. You have various lines popping, but mostly they were little lines. But as they popped, the Samus Star line got hotter and hotter. The system was hanging by a thread at that point, but it was still hanging in there. But when the Samus star line popped at 1605, then stuff really started to go fast. So now we have low voltages spreading across the region. Of course, if you know much about power, you know that power is equal to voltage times current. So as the voltage goes down, the current goes up. And as the current goes up, the resistive losses are I squared R. Current goes up, I squared goes up with the square current. The lines start heating up more and more. Eventually they sag into something. There were actually zone 3 relays, which are talked about in the report, that were starting to trip lines. So we started getting the classical cascade occurring, but it occurred over many minutes, on the order of about from, let's say, 3:36 or 3:35 in the afternoon to about 4:10. So you had 35 minutes of action. One of the interesting aspects of the blackout was it allowed us to crash test the system. Certainly not a deliberate crash test, but it was a crash test nonetheless, and it let us figure out, are the DC stands for a power flow solution approximation method, where we approximate the system using a very simpler system. Turned out that those things were pretty good. I was actually very surprised at how well the LODFs worked, even when you had a very stressed system. So for the mathematically inclined in here, this is talking about how well these LODFs are approximating the results. And it turned out they were very good. I was quite impressed, at least up until we started getting very low voltage. DC approximation assumes that the voltage on the system is unity. And by the time you get into about 1546, the unity voltage was not a good approximation. So LODFs and the flow gates associated with them, I thought were very reasonable. Even after more than a dozen contingencies with many voltages below 0.9 per unit, the purely DC LODFs were given a pretty good result. So for those of you who work with DC power flows, they're not too bad. Up until about 1610, the system was actually quite well behaved mathematically. Okay, power flows were reasonable. The dynamics didn't start to dominate until right at the end. How the flow redistributed through the system was how we would predict it. It was essentially linear. All our methods for predicting systems worked quite well up until 1610. Here's a couple of figures from the blackout report that are just going to summarize the last couple of minutes of the system before it collapsed. We've been mostly focusing on Northeast Ohio. The black lines there show the lines that tripped. We've got 3 of the paths tripped there into Ohio. Actually, I think all 4 of them were tripped at that point. So now the Cleveland area was hanging on by paths coming in from the east along Lake Erie, and then from the rest of Ohio, they're kind of on the western part of the state. Well, one of those starts to trip. So now you get lines tripping about 4 minutes later. We lost the supply into the Cleveland area from the south west. Then what happens is we start getting frequency issues on the system, and the generators start to trip. As the generators start to trip, we're getting an imbalance between power and load, and that means more power has to be injected into the system. By 1610-37, we have a pocket of the Michigan-Ohio system disconnected from the rest of the United States. It was being served only through our friends in Canada. So Ontario was trying to supply the Detroit area, the Cleveland area, the Toledo area, and they tried valiantly for a few seconds. So you suddenly had this big power swing that the power flow swung through the New York-Ontario system. The folks that went and visited the New York ISO for the investigation, for New York, it was a couple seconds. That was the extent of the blackout for them. Ohio, it'd been playing out over an hour. in New York, the operators didn't even have a chance to get out of their chairs. This power swing occurred, and they're like, what? And this is the response to the system, and now this bottom line there is in seconds. That's 10 seconds. You have power flows on the Ontario-Michigan interface going between 4,000 megawatts positive to minus 2,000 megawatts negative within a couple seconds. This is a real cool dynamic phenomena. It was less cool if you were a customer because your lights would be going out very soon. But from an analysis point of view, this is pretty cool. There were a lot of folks in the NERC investigation who spent a lot of time trying to figure out what was going on. We got a lot of data with the blackout investigation, but we did not have a complete state estimator model of what was going on. So what I've shown you are just best guess reconstructions. A lot of people at NERC spent a lot of time trying to reconstruct what was going on during this time period. So these are actual traces, but they tried to figure out what was going on. Ties from PJM to New York open 16/10/44. So the New York event is over in a couple seconds. New York goes black. Various places hold on for a little bit longer, but eventually that whole area starts to break up and go black, like what we saw on the initial satellite picture. PJM actually, for the most part, stayed together. People have speculated why that is. Certainly the fact that PJM had a 500 kV system where the part that blacked out was 345 kV might have had something to do with it. AEP's system had a lot of 740 or 765 kV in it. It's a much stronger system, so it did not black out. Whether this thing could have spread to the rest of the Eastern Interconnect, it obviously didn't, but I think it came pretty close to being a major, or not much bigger than 50 million people event. So what are some thoughts on our current need? I do want to say the blackout report was a wonderful report. The people that wrote it, and again, I did not write it, it's very accessible, and I would commend all of you to read that report. Particularly if you're not a power engineer, it's something that you could easily understand. Things like reactive power are very well explained in it, oscillations, all sorts of really good stuff in there. I also want to say that DOE responded very quickly in getting folks out into the field. 2 days, I was notified by DOE that would I be available 2 days afterwards. So they got folks out there really fast. That's key if you want to get information about what people are thinking. What were you doing when? You need to get out and you need to talk to them. DOE did a wonderful job of getting people out in the field. There were people talking to AEP and people talking to, Doug and I were talking to First Energy. A couple days later, we got there on Monday night. I will say that when we were there, you got to keep in mind there'd been a blackout. The folks we were talking with had spent a lot of time reconstructing that system. Okay, so they were the ones who put it together. They spent a long time putting that system together. When we were there, a lot of the nuclear units had not come back online, so we were very concerned that we don't want to cause another blackout. Okay, so we were making sure we'd say, we can only talk to this guy if he's available. First Energy did a wonderful job of making the people available to us, and they had a long 5 days. So here I am and Doug sitting in a room saying, okay, at 15:35, 5 days ago, what were you doing? And of course they had better memories because it was a dramatic event, but they had spent a long time putting together that system. So the investigation, very positive things to say about people involved in it. What's been surprising to me is how little has been written in the public technical literature about the blackout. If you look, there are reports out there, but a lot of the data has not gotten out to researchers. There are a lot of researchers who would like to study those cool dynamics that went on when the system broke up. But researchers have a hard time getting access to the data. I know Bob Thomas and some folks at Cornell have been working to try to set up a library, but that has not worked out. The data, for the most part, is not available, which I think is too bad. I think there's obviously confidentiality issues associated with it, but I think it could get more publicly, at least available to people that can demonstrate a need to know to study some of these cool things. What we're finding is vendors have little incentive to publish results. A lot of cool stuff has taken place since the blackout. But if you look in the public technical literature, you don't see a lot of papers on it. There's presentations, but usually it's just a slideshow. There's not the papers there. They just don't have the incentives. I think there's way too little research going on in power system human factors. This was a human factors event. Doug Wiegmann really picked up on that when we were there, and he was pointing to me, hey, they couldn't see the strip charts because they're over here. And we were talking about a lot of human factors issues. We need more research in that area. I will say most of the technical journals are reluctant to publish human factors issues, at least in the power system area. I know that from personal experience. Data used to model interconnect-wide system studies still have significant problems. If somebody said to me, do you have confidence that we've addressed all the issues? We've addressed a lot of issues, but I think there's still some concerns out there. I was just at a meeting earlier this week. It was a WECC group that's looking at how do we model wind turbines for interconnect-wide studies. We don't have adequate models for wind turbines, and there's 40 gigawatts of wind resources in the U.S. right now. We don't have adequate models. I will accept GE because GE's been wonderful with giving us models. The models actually represent GE quite well. Vestas was at the meeting, and they're making much more data available, so hopefully we'll be making progress on that. We're in a time period where the power grid is rapidly changing. This can result in some operational surprises. And surprises, we don't know what they are, but my feeling is voltage stability and renewable resources are going to be issues in the near-term future. I had the opportunity to have dinner with the CEO of a major EMS manufacturer in Europe, and people say, well, Europe's got all this renewables integrated in. What he was telling me is, yeah, they do, and he's really concerned because his company writes the software that is their energy management systems, and if they mess up, it's his reputation. And last, we need people with a deep knowledge of cyber and power systems. We need cyber guys that really know power guys that really know cyber, and that's what we're working on training up here. Okay, thanks.
Since Tom was really good with time, we have time for questions, both remotely and in the room here. I know we have a pretty big crowd on remotely.
For those online, if you indicate in the WebEx chat that you have a question, we'll relay your question to the presenter.
Why did those alarms hang?
Technical issues. I don't know the details on why the alarms hung. There was quite a bit of investigation, who had what patch when, what was the cause. Some of it's detailed in the blackout report, but I don't know the exact detail on why they hung. We did try to figure out whether they had hung before, and I was just looking at the blackout report to see what made it into the report. What the report says is that they indicated their alarms had probably hung before, but not to the extent where it was slowing down the operation of the system. And they've since replaced that system, so it's not a current concern.
We have a question from online. Is there a way to play with a state estimator on a basic PC?
Certainly a basic PC. I mean, PCs can be pretty high level, so PCs can certainly run state estimators, so yes.
So, Tom, situational awareness, as you pointed out at the beginning, was a really key part of all of this. Can you comment with NASB and wide area measurement systems and so forth coming online, whether you think the direction we're going will solve those kind of problems, or whether there's a different direction to go, or what's missing?
Well, I think we're certainly moving in a good direction. And just if you contrast the slide I showed of First Energy's control center right now, I think it's a very robust control center. And I've had the opportunity to visit there since. PMUs are certainly going to provide us with more information. The challenge is to us as researchers and to the software developers to make adequate use of that information. What we don't want to do is inadvertently overwhelm people with data. So having more data available is a good thing as long as you use it effectively. Like I said, I think we need more research in human factors. I would like to get Doug Wiegmann, and there's another guy back involved in power system research. Doug, after the blackout, he took a sabbatical leave and went up to Mayo Clinic to actually study human factors in heart surgery. So he's the generic human factors guy. Now he's at University of Wisconsin-Madison, my alma mater. But as you start showing PMU information, more information to the operators, let's do it in a way that's human-friendly.
From online, we have a question. What would a cybersecurity expert have been able to do in 2003? And what use would a cybersecurity expert have in 2011?
Okay. Well, what they could have done in 2003, I'm not sure, but it was certainly an IT issue that led to the genesis of the blackout, because if the alarms hadn't hung up, they would have had at least a heads up. Whether that could have prevented the event in 2003, I don't know. Right now, what we're doing is things have changed quite a bit from 2003. We know in 2011 that cyber concerns are a real issue. We've been working on that at University of Illinois through TCIP and currently through TCIPG to address those issues, better protect the system. We've seen with the Stuxnet worm or whatever it is getting into the computers, what they can potentially do. So I think there's people that need to understand both sides, not just the power side, not just the cyber side, but a combination thereof.
And also a question, what research or advances have been made in visualization tools for operators?
Well, that one is very dear to my heart. A lot of work in visualization went on actually in the 1990s, and going back to the PC question, the reason for that was because in the 1990s the PCs became available so we could take bright university grad students and apply them to the power system visualization problem. One result that came out in the late 90s, which I've shown extensively here, is contouring. We've now realized that you can show power system information like voltage profiles pretty well with contouring. What we're working on right now is how do we best convey PMU information, such as bus angles. We've seen some slide sets that show bus voltage angles using pie charts. Well, is that the best way to do it? Using dials, is that the best way to do it? So map boards are an area where there's been visualization research going on. What to show on the map board, how to show it. Different utilities take different design approaches. I did, along with one of my grad students here, Sudipta, we did a project for EPRI where we did a survey and assessment of visualization technologies. And different utilities use vastly different approaches.
So not being a power engineer,
I won't hold it against you.
How much does it take to really trip one of these transmission lines? Now, I asked the question in the context of, advanced metering infrastructure where, one node might have the ability to control, 200 to 400,000 amps of service with their local load disconnects and so forth.
What do you mean? To trip a line, all you need is a tree to come in contact or get close enough to the line to trip it. That first line that tripped in the August 2003 event was loaded at about 37% of its rating. So it was not overloaded. Then usually when a line overloads, the conductor heats up and it sags down. If there's a tree underneath it and it gets close enough to arc, then it'll cause what we call a ground fault, and you'll get current flowing, and that current will cause the circuit breakers to trip. You can get very high fault current, but the circuit breakers can easily interrupt that.
Sure. I guess I asked a question in a downstream transient condition. If you're toying with the loads, could that cause one of these big transmissions to trip?
The line like that would have been carrying probably on the order of maybe 500 megawatts. So if you're toying around in your house and you short the circuit on your toaster, you're not going to trip a 345 kV line.
I think the specific attack he was talking about, which I call the CNN attack because they were calling people up asking about it, is what if you do something that causes a whole bunch of meters to issue a disconnect notice at the same time? And how many meters would it take? Now, you don't have to answer that question if you don't want to, but that's what CNN's been asking people.
To cause a real system disturbance, you would need maybe tens or hundreds of thousands of meters going at once. You have to have a shock. The power grid is pretty good at absorbing shocks. After this event, some people got in the news talking about how fragile our power grid is. Our power grid is not fragile. It gets hit by lightning all the time. Lines go out and it keeps on ticking. If you lose 100 megawatts of load, okay, we've got loads in the system where you'll get 200 megawatts from an arc furnace coming on like that. So the power grid can handle some pretty significant disturbances. So, could you do it if you got all of Cleveland to disconnect? Sure, if you got all of Cleveland to disconnect. If you got 1,000 houses, it's not going to have a big impact.
Okay, we'll wait 1 minute to see if there's a last burning question. I don't see one here, not there. Well, Tom, thank you very much. I think that was a really enjoyable and fascinating seminar for all of us. We appreciate you doing that. And for all of you here and online, our next public seminar will be the first Friday of next month. And we look forward to seeing you then. Thank you, Tom.
Thanks.